Welcome. This is Coach Dorf. Today we're going to talk about the chain rule. This is going to allow us to take derivatives of more complicated functions. All right, so to do this, let's review a few ideas first of all. If I have a function f of x equals x to the seventh, I know by the power rule that its derivative is 7x to the sixth. Likewise, if I had the function g of x and it was 2x cubed plus 5x, its derivative by the chain rule or by the power rule would be 6x squared plus 5. All right. What about the function capital F of 2x cubed plus 5x to the seventh? What about its derivative? Now, some of you may notice here that this capital F is a combination of the little f and the little g of x functions. And that's exactly true. Capital F can be written as the composition of little f of g of x, which means I put g of x into little f. So that means when I write this, I can replace the g of x with the 2x cubed plus 5x. All right, so what I'm doing here is replacing the g with the f because we have g of x equals that. And then I now take what's inside that parentheses after the f, so that 2x plus 3, 2x to the third plus 5x, and I put that in for the x part of f. In other words, instead of having just an x here and here, we're now going to replace that with this 2x cubed plus 5x, and that's going to go there. So we're putting this, we're putting in the 2x cubed plus 5x into the x part here, and then that's going to come back and would give me this. So the main idea here is that this capital F that's more complicated than functions we've seen before, is the composition of two other functions. And this then was going to allow us a formula or an approach to take the derivative of this more complicated function. And the idea here is the following. If capital F be written as a composition of two functions, so g of x is inside of f, then derivative of capital F is going to be the derivative of little f evaluated at g times the derivative of g. That's the idea there. And this is known as the chain rule. So let's see how this applies in this situation. So again, if we let me do it this way, we're going to call this an example. So example, capital F equals 2x cubed plus 5x to the seventh power. Find its derivative. So to do that, I'm going to notice that capital F can be written as little f composed with g, where little f is x to the seventh and g is this 2x cubed plus 5x. I like to call the g the inner function, what goes inside, and the f as the outer function. All right. So by the box above, all right, that's this meaning this box up here, we know that the derivative of capital F is going to be little f evaluated, the derivative of little f evaluated at g times the derivative of g. So what is, we saw earlier here that little f, derivative of little f was 7x to the sixth. The derivative of little g is going to be 6x squared plus 5. Use that fact. So now we're going to have 7. So the derivative of capital F is going to be the derivative of little f, which is going to be 7 parentheses to the sixth times the derivative of little g, which was 6x squared plus 5. And the question is, what goes inside this parentheses here after the 7? And what goes in there is g, and so that's going to be 2x cubed plus 5x. So the whole answer is going to be 7 times 2x cubed plus 5x to the sixth times parentheses 6x squared plus 5 close parentheses. That's a formal way to do it. Another way to do it is I like to think of this as a box. So I'm going to call this approach A, and then here's approach B. Both of these ways work. Okay, I can think of f, again, f in this case was 2x cubed plus 5x to the seventh power. So I can think of that as a box to the seventh power. where inside the box is the inner function. That's why I like to call G the inner function. So inside my box, I have 2x cubed plus 5x, and then outside I have my box with to the 7th power. So inside is g of x, which is 2x cubed plus 5x. All right. So then how do I use this to take the derivative? Well, the derivative is going to be then, I'm going to take the derivative of the box. So it's going to be the derivative of f with the box times the derivative of box. Okay, that may be a little confusing that way, but let's just go ahead and apply it. So I'm looking at my box, color that in red here. So what's the derivative of that? Well, I've got a box to the 7th. So by the power rule, I bring down 7. I take my box and I put it to the 6th power because I reduce it by 1. And now by the chain rule, I need to take the derivative of the box. And again, what's inside the box? Inside the box is this 2x cubed plus 5x. So my next step is I'm going to have 2x cubed plus 5x to the 6th power times the derivative of what's inside the box, which is going to be 6x squared plus 5. And that's my answer. And notice that answer, this one matches this one. They're the same. And so you can use either approach. They both work in doing this. All right, so let's apply this to some more examples. And we're going to start off slow with these examples so that you can see this idea, what the inner function is and what the outer function is. So the next example will say, find the derivative at capital F for capital F equaling the sine of x squared. All right, so what's my inner function? What's my outer function? Well, my outer function is sine x. My inner function is x squared. So this is inner, this is outer. And I notice that when I do f, little f composed with g, that means I'm putting g into f. So g is x squared. Again, here's my g. So I go up here, down there. And so now I've got, I want that to be black there. And now wherever I go back to my f function here, which is in blue, there's my f function. And wherever I see this x, I want to replace that by what's inside here. So doing that, I'm going to get sine of x squared. And that matches with what I have up here. So I've got the correct inner and outer functions. So what is the derivative? By doing that main boxed idea I had at the very beginning, remember that was this idea. I'm going to highlight this in some color, let's say pink, because I don't use pink very often here. There's that pink box. That's the idea we're going to be doing here. So the derivative here was going to be of capital F is going to be little f prime evaluated at g times g prime of x. So what is the derivative of little f here? So we'll just do this. So f is sine x. So its derivative is cosine x. And g was x squared, or is x squared, and its derivative then is 2x. Okay, so we're going to use those. So now I'm going to have f prime, this part first. So I'm going to have f prime, which is cosine of big parentheses. I'm not going to put the x there because I want to put the g in there. So let me just put that in there. It's going to be g, cosine of g, times g prime, which is this. So that's going to give me 2x. So this comes from that part, and this comes from that part. All right, and now I just put in what is g. G was x squared, is x squared, and so I get this. And then more common to put the 2x first, and so the final answer would look like this. All right, so that was, again, using kind of the method A there. And now I'm going to use the box method. So I'm going to think of f of x, which is sine of x squared. So that's the sine of box, because inside the parentheses is my inner function, my g, and that's where my box goes. So then the derivative is going to be the derivative of box. What's the derivative of sine? What's the derivative of sine? Well, derivative of sine is cosine. So I put cosine box times the derivative of box. And again, what is inside the box? G of x inside the box is g of x, which equals x squared. That goes in all of these. So when I write that in, I've got cosine of x squared, because that's what's inside the box. And then I take the derivative in this part right here. I'm going to take the derivative of what's inside the box. And when I take the derivative of x squared, it's 2x. And so then again, I'll put the 2x first, and I get 2x cosine x squared. And we see once again, very nice, that the two answers are the same, which is what we want. Now, when you do this, you don't have to do both of these methods. You can choose which method you like. I'm giving you two ways to do it because some people like the method A and some people like method B. Hope is that you can do one of these, do it correctly, and then as you do these more and more, you actually won't even need to consciously think of doing either method A or B. You'll just do it automatically. All right, but this, to get started, to get familiar with this, because this is a new idea, many of you haven't seen this before, you can either use method A or B, whichever one you feel more comfortable doing. All right, let's do a third example here. So in this example, we're going to find the derivative of capital F for capital F equaling e to the square root of x. So you should think at this point, if you're not familiar with this type of approach here, you should think about what is your outer function and what's your inner function. So little f, and I'm going to call that e to the x, and that's my outer function. And little g is going to be the square root of x, and that's my inner function. And so when I compose little f with g, that means I'm going to have little f, and I'm going to put in square root of x in for wherever I have x in f. So here, let me do a different color there. So because of this here, that's why I'm going to get this. And then here, I'm now going to take, what is f? I've got this x here, this x here. So I'm going to put this in for x. And so in my f function, I'm going to have e to the square root of x. All right. And these two match. So that's what I'm going to use. So if I'm doing method A, then the derivative is going to be little f prime evaluated at g times g prime of x. That's the idea in that pink box at the very beginning. All right, so I want to find out what if f is e to the x, then the derivative of that is e to the x, because that's the same. And g of x is square root of x. What is its derivative? Well, that's going to be, it will be 1 over 2 square root of x. Let me just go into a little bit more detail about that. I can write g as x to the 1/2 power. So when I take its derivative, I do the power rule, I get 1/2 x to the negative 1/2 because I subtract 1 from a half. And then I can write that as 1/2 1 over x to the 1/2 power, which is the same thing as 1 over 2 square root of x. Some of you have done this enough and feel comfortable enough with this that when you have the derivative of the square root of x, you just automatically know that that's going to be 1 over 2 square root of x. And that's great if you're at that stage. If you're not at that stage, you can keep doing it, and it may be soon in the future that you'll get to the stage that will just make sense to you. All right, so now we're back here. Let me circle where we're at. We're back here, and we want to apply these ideas, the results that we just got, to this. So what is f prime? F prime is e to the x. So we're going to put in e to a big parentheses here because we don't have just an x, we have g to the x. So really this is going to be e to the g of x. All right. And then I have to put in what g prime of x is, which is 1 over 2 root 2. That's coming from this part right here. So g, that goes here, and then we get this over here. All right, and from there we have g, and what is g? G is square root of x times 1 over 2 square root of x, and I could write this then as 1 over 2 square root of x e to the square root of x. There's other ways you could write that. Notice that you cannot, in this final answer, in the boxed answer that I put there, you can't cancel out the square root of x's. You have to just leave the answer like that. Now, if I do the other technique where I'm going to do the box method, we have again our function e to the square root of x. That's our original function. And I'm going to think of that as e to the box. So what is the derivative? It's going to be the derivative of e, which is e, and then I put the box there, times the derivative of the box. All right, and what goes in here? So inner function, or inside the box, inner function is g of x, which is square root of x. That's what's inside this boxes here. All right, so I'm going to have e to the square root of x, because that's what's inside the box, times the derivative, square root of x. And from what we just did up above, we know that the derivative of square root of x is 1 over 2 square root of x. And so I get this as an answer. And again, my two answers match, which is really nice to have. So let's see, let's do another example. All right, so we're going to differentiate capital F of x, which is going to be the cube root of 5x squared minus 4. And I look at this one, it's a more complicated. I can't use the power rule on this. Can't use the product rule. Can't use the quotient rule. It's more complicated, but I can write this capital F as the composition of two functions. All right, so let's see, what's my inner function, what's my outer function? Well, I'm first going to note that capital F can also be written as parentheses 5x squared minus 4 to the 1/3 power. So the cube root is the same thing as the inside being to the 1/3 power. So my outer function is going to be x to the 1/3 power. So that's my outer function. My inner function is going to be 5x squared minus 4. And I can check, you don't have to do this every time, but I can check that if I compose those two functions together, I'm going to have f, and then inside of f, I'm going to put in what g is, which is that. So again, I go from here, up here, and then there. You don't have to mark this. I'm just marking this to help people make sure everybody understands. I don't need to, I wouldn't do this normally, but again, just to trying to make it clearer for everybody. And now I'm going to take f and put in the 5x squared minus 4 into wherever x is for f. So remembering that f is this, and inside that I've got, here's my x and here's my x. So when I apply that here, I'm going to have the inside part to the 1/3 power. And that is my function there. So I got my function described as the composition of two, my original function. So the derivative of that original function, the derivative of capital F, is going to be little f prime evaluated at g times g prime of x. All right. And again, work out what f, the derivative of f and g are. So f is x to the 1/3. So when I take its derivative, then that's going to be 1/3 x. And now I have to subtract 1 from 1/3. That's going to give me negative 2/3, which is often written as x to the positive 2/3 power if I put it in the denominator. You can also, some of you, and you write that as the cube root of x squared, and you can, but I'm not going to do it right now, but that's perfectly fine thing to do. And g of x, if g of x is 5x squared minus 4, then its derivative is 10x. All right, so we're going to use that. So now I've got f prime. So f prime is this 1/3 parentheses to the negative 2/3 power. I'm using this idea here. So that's what's coming down here. And I leave the big parentheses there because that's where g goes. Well, maybe I should just write that. There's g, and then times, what do I have? I'm going to times g prime, which is 10x. And that here is what goes right there. And then if I write that out, now I've got 1/3. I replace g there, which is 5x squared minus 4 to the negative 2/3 power times 10x. And then rewriting that, I could put the 10x on the top, put the 3 in the bottom, and I could put the 5x squared minus 4, which is in parentheses, to the 2/3 power in the denominator, and I get that. I could also do this by the box method, but I'm not going to on this example. I'll just go back and forth between not doing the box and doing the box. But this is the correct answer going through on this method. So now let's do another example. We're going to find y prime for y equals to e to the negative 2x cosine of 4t. Sorry, y equals e to the negative 2t times cosine 4t. Now, the first thing I notice about this problem is that when I write out y is e to the negative 2t times cosine of 4t. So I've got the product of two functions there. So we have to use the product rule, right? I have e to the negative 2t is one function, cosine of 4t is the other functions. I multiply them together. So by the product rule, what do I have? We've got y prime is the first times the derivative of the second. And notice I'm using ddt here instead of dtx because my variable in this problem is t, right? And then I have the second cosine of 4t times the derivative of the first, which is e to the negative 2t. So now I need to figure out what are those derivatives. So we're going to do a little box here. So what is d dt of cosine of 4t? This is where I have to use the chain rule. So I've got this cosine of 4t, and let's just call that capital F of t. That's really then going to equal the cosine, that if I let little f equal cosine of t and little g, it's going to equal 4t. Then when I do composed with g of t, I'm going to get cosine of 4t, which is capital F of t. So the derivative, I'm going to do this one by the box method here. I'm going to have cosine of box. Oh, sorry, didn't write that notation right. I want to take the derivative dt of cosine of box. When I do that, what do I get? Well, I take the derivative of cosine. What's the derivative of cosine? It's sine. So I put sine of box times derivative of box. And what goes inside the box? So inside the box is this g of t here. And so now I've got sine of 4t. And what's the derivative of 4t? It's 4. So I can write this as 4 sine of 4t. So that was the first part. I'm going to circle that in purple. And now I also need to find out what is the derivative of e to the negative 2t. Again, we need to use the chain rule. So I have, I'll just call this, what do I call this? I'll call this h. Capital H of t is e to the negative 2t. So what is my inner and outer functions? My outer function is e to the t. My inner function is negative 2t. So that if I do f of g of t, that's going to be e to the negative 2t, which is f capital H of t. All right, so derivative of h is going to be ddt of e to the box, which is going to be e to the box, because the derivative of e to the x is just e to the x times the derivative of box. And what goes inside the box? Inside the box is this negative 2t, so that when I continue doing the derivative, then I've got e to the negative 2t times negative 2, or just writing it as negative 2 e to the negative 2t, and that's that answer there. Some of you have noticed here that whenever I take the derivative of e to some function, no matter what the exponent is there, the answer, the derivative of that is always going to be the derivative of the exponent times e to the original function. All right, so in this one, I have e to the negative 2t. So I look at the exponent, negative 2t, I take its derivative, I get negative 2. So then I say the derivative is negative 2 times e to the negative 2t. If my original function were e to the x squared, then the derivative of that would be, derivative of x squared is 2x. So the derivative of e to the x squared would be 2x times e to the x squared. If my original function was e to the 1/2 x, then the derivative would be 1/2 e to the 1/2 x. All right. If you see that, then you can use that idea because that will always work. All right. Now going back to what we originally had up here, we had this one for the derivative. So I'm going to write that back down here. That's y prime. Y prime was equal to e to the first times the derivative of the second plus the second times the derivative of the first. All right, and so now what do we have? We know that the derivative of cosine 4t was from up here, 4 sine 4t. And then we've got cosine 4t here. And then we have the derivative of e to the negative 2t, which here was negative 2e to the negative 2t. So you have that as an answer. And that's a perfectly fine answer. In some cases, oh, you know what? I made a mistake up here. I'm going to go back this. I'm sure that you all saw this and you're probably thinking, what's loony with Coach Dorf? when I was back here at this stage here, I said, what's the derivative of cosine? And I said it was sine. That's not right. It should be minus sine. So this should be a minus. This then should be a minus. So when I do this, I should have a minus here. That makes much more sense. It makes me feel good. And now when I look at this, I can say, oh, well, let's see. There's something in common here that I can bring out. I can bring out a -2 e to the -2t, because everything, the part before the plus has a -2 e to the -2t, and the part after the plus also has that. And so when I do that, then I end up with a 2 sine 4t plus cosine 4t. And that would be an answer probably you would see in the back of the book, because you'd be factoring that out. Let me just reiterate this comment here about the mistake I made. We all make mistakes. That's just part of life. Okay. It's not a problem that you make a mistake. What you want to do is you want to learn from your mistakes and improve. I'm okay that I made a mistake here. Hope you guys are okay with the fact that I made a mistake. I caught my mistake and we corrected it here. I think it's good for you to see that I do make mistakes. All right. I'm not perfect. All right. And it's okay if you guys make mistakes, but as you practice, you'll get better and better. So you'll make less mistakes. Next, let's do another example. This one's going to be a little bit harder here. So what's this example going to be here? I'm going to look at y is going to equal secant cubed of 2x plus 1. Find y prime for that. So some of you may say, well, I could write secant cubed as secant times secant times secant and do the product rule a few times, and you could get the correct answer. In the long term, it's easier, I think, to do the chain rule here. All right, so in doing this, I'm first going to notice that I'm going to write my original problem. Secant cubed means that I have secant of 2x plus 1 all to the third power. All right, so if I do the box method, then I've got y is going to be equal to the box cubed, right? And inside the box is the secant of 2x plus 1. All right, so now when I take the derivative, y prime, that's going to be about 3 box squared times the derivative of the box. And again, inside the box, we've got that secant 2x plus 1. And if I write that out a little bit, then I've got then the secant 2x plus 1. This 2 up here, then I can write down here as just a square. So it's secant squared. And then I've got the derivative of secant of 2x plus 1. Now, what makes this problem a little bit more difficult is that the derivative of that secant 2x plus 1, I'm going to have to do the chain rule again. So we have to use chain rule again, a second time to do this. So I'm going to look at this as, I want to call this capital F of x to equal secant of 2x plus 1. So that can be written as the secant of box. So then the derivative is going to be, what's the derivative of secant? Well, that is secant tangent. So I'm going to have secant box tangent box times the derivative of box. And in this case, what do I have inside the box? Inside the box here is 2x plus 1. And that's the same in all of these. So I'm going to have secant of 2x plus 1 tangent of 2x plus 1 times the derivative of 2x plus 1, which is just 2. And some of you probably want to write that as putting the 2 out front. So it looks like this. So now I've got 3 secant squared 2x plus 1 times the derivative of secant of 2x plus 1. And we just saw that this part here, that is equal to this. So I'm going to end up with 3 secant squared 2x plus 1 times 2 secant 2x plus 1 tangent of 2x plus 1. That's coming from here. And now I've got that 3 and the 2, so I'm going to multiply those together. And I have a secant squared and I have a secant. So when I combine those, I get a secant cubed 2x plus 1, and then I have a tangent 2x plus 1. And that's my answer there. Let me show you one example of a different type of problem where you're not necessarily given a function, but you're given a values of functions. So in this example, and this example is it's similar to example 8 in the lecture notes, but if I have a function, let's call it h, we're going to write it as f of g, then again, by that original box at the very beginning that was in pink, the derivative of h is going to be f prime of g of x times g prime of x. And if I want to value h at a certain value, let's say 1, then I'm going to put 1 in for x. And so I need to compute the value of h prime of 1. I need to know what g prime of 1 is, g of 1, g prime of 1, and then f prime of g of 1. So we need to know g of 1, because that comes from here. We also need to know g prime of 1. Then we need to know what f prime of g of 1 is, right? This part here, and this gives me that. All right, so sometimes you have problems like this, and you'll be given a table. So let's look at this problem here. Here we have this table of values. Let me center this a little bit, all right? And again, we wanted to find g of 1. So to find g of 1 here, I look at this table, and I notice on the far right side, I have far right column, it says X, and then it has 1, 2, and 3. So to find G of 1, I go to the third column, and it has G of X, and I find the intersection of G of X going down and 1 going across, and I see that G of X, G of 1 is 3. So I wanted G of 1, and G of 1 was 3. I also needed to know G prime of 1. So I look on there and I see that G prime of 1, I have the row that has 1 on the left, and go all the way to the far right, and I see g prime of 1 is 2. And then I want to find what f prime of g of 1 is. So that was f prime. We saw that g of 1 was 3. Now I'm going to look, I have to find f prime of 3, because we wanted f prime of g of 1. So f prime of 3, and I see that looking at the very bottom row, and going down from f prime, I see that is 6. So now if I go back to my iPad, then I've written in those values from the table. We need to know those. And we got these, so we can get these from the table. And so h prime of 1 is going to equal, again, f prime of g of 1 times g prime of 1. And that's going to be f prime of 3 times 2, where these are coming from. I'm putting this in for the 3 here, and I'm putting this in for the 2 there. And then this is going to be a 6 times 2, and I'm doing that because this goes in here. So I end up with 12 as my answer. Now that's hopefully you can see the how to do this one. It's not really clear because I don't have the table there, but in my lecture notes in example 8, as I mentioned, there's another problem that's just like this that will help you solve this. And let me end up by just telling you one last formula. If you have the derivative of a to the x, that's going to be 2 to the x times natural log of 2, all right? And so that matches if I do the derivative to the x, that's going to be e to the x times natural log of e, but we know that natural log of e is 1, so we get e to the x. So that works really well. And so then a final example of this is if I wanted to differentiate, let's say y equals, oh, sorry, I made a mistake again. Sorry about that. This is not right. This is a to the x times natural log of a. So if I now have y equals, let's just say 4, we'll say 3x minus x squared. Then when I differentiate that, I'm going to use what's in, I'll make this a pink box too. So we have 2 pink boxes. Both of them are important. So by the pink box, y prime is going to equal 4 to the 3x minus x squared. That stays the same, times the natural log of 4 times, and by the chain rule now, I have to do the derivative of that exponent. And so I get 4, 3x minus x squared times natural log of 4. And then the derivative of the exponent is going to be 3 minus 2x. And some people would like to write this, perhaps just switch the order of this. We could have 3 minus 2x natural log of 4 times 4, 3x minus x power. Hopefully that helps you, gives you some background on this.